take a look of the chemical vapor deposition of layered two-dimensional molybdenum silicon nitride materials. Two-dimensional Danavans layered materials have unique property and broad application in the field of energy environment and other fields. And currently, we widely study two-dimensional layered materials such as graphene, boronitride, transition metal chalconite, and also exploring two-dimensional layered materials without knowing three-dimensional materials can be greatly expand the physical properties and applications of two-dimensional materials, which has an important, significant, and practice value. At the present, several two-dimensional materials preparing methods have been developed, which can be roughly divided into two categories, top-down and bottom-up method. The top-down method uses external force, such as exfoliation and intercalation, to make the bulk layer materials to the atomic level. In this method, it is necessary to overcome the weak Danavans force between the layer, and the bottom-up method uses the precursors to preparing two-dimensional materials through the direct surface growth or chemical reaction, usually on the substrate. Chemical vapor deposition is a typical bottom-up method for preparing two-dimensional materials. Specifically, it is a process in which one or more precursors undergo a chemical reaction on the solid substrate in a high-temperature zone. Under the transport of a protective atmosphere to synthesize two-dimensional crystal and their films. In the CVD reaction system, the morpholate size, number of the layer, and the crystal quality can be controlled by adjusting the precursor reaction source, growth substrate, and the growth environment. A new method attracts people's attention. This work creatively introduced silicon in the CVD growth processing of non-layered molybdenum nitride, and then activate the high-energy site on the surface of non-layered molybdenum nitride through silicon, thereby changing its isolate growth mode. The researcher used a CVD method with copper molybdenum foil bimetal laminate as the growth substrate. The copper foil is melted and solidified at a high temperature. A silicon source is introduced, and ammonia gas is used as a nitrogen source to preparing a monolayer molybdenum silicon nitride single crystal and a centimeter scale molybdenum silicon nitride polycrystalline film. Next, high-quality transfer was achieved by chemical etching the copper foil. In addition, multi-layered molybdenum silicon nitride crystal was obtained by increasing the ammonia flow. The molybdenum silicon nitride monolayer is formed by 7 layers of atomic stacks, and it can be regarded as the composed of 2 bond layers. And if the layer and the 2 adjacent nitride layer forms the basic structure unit of the silicon nitride.
The unique structure gives unique physical and chemical properties. Studies have shown that the single-layer molybdenum silicon nitride is a p-type semiconductor with an indirect band gap of -1.94 electron volt. Raman resonance effect under 532 nanometer laser. High light transmittance in the visible light range. At the same time, it has excellent mechanical properties and good chemical stability. The growth of molybdenum silicon nitride gives the direction of preparing new two-dimensional layered materials without three-dimensional matrix materials, and opened up a new family of two-dimensional layered materials. Based on the work of it, the two-dimensional tungsten silicon nitride crystal was successfully prepared. Further theoretical calculations are used to predict more than 10 new two-dimensional ternary layered materials that can exist stably. This forms a new family of two-dimensional ternary layered materials.
Let's take a look at the CVD growth mechanism of two-dimensional molybdenum silicon nitride crystal lines. The growth of new ternary layered material transition metal silicon nitride can be decomposed into two parts. The first part is the growth of ultra-thin transition metal nitride, and the second part is the introduction of passivating element silicon. The traditional CVD preparing is not suitable for preparing ultra-thin transition metal nitride. These methods can result in uneven nitridation at different thickness of transition metal sheet, and there is no obvious interface between the transition group metal nitride and the transition group metal body attained by nitriding. In order to solve the above problem, the researcher preparing ultra-thin transition metal nitride using bimetal laminates as the substrate. The key in this method lies in stacking a second layer of metal on the surface of the transition metal as a diffusion barrier. Another fact is how to realize the supply of silicon, which was the first proposal in the field of preparing two-dimensional materials by CVD. The reason for this is when deposing materials, layered growth tends to occur with a smaller surface energy than the growth substrate. Passivation sites with a higher surface energy to promote layer growth are the key to uniform growth of TMC or TMN films to the monolayer limits. Therefore, layer-free two-dimensional molybdenum nitride can be growth into two-dimensional dead ones, molybdenum silicon nitride, which have a normal layer film of centimeter level, can be regarded as the molybdenum nitride layers, sandwiched between two silicon nitridation double layers.